In this video, we're going to practice modeling with arithmetic sequences. So here's the first problem. A concert stadium has their seating designed such that each row behind the previous row has 3 additional seats. If the first row has 20 seats, then how many seats will the 12th row have? Why don't we start by drawing a diagram of this situation here. So maybe there's the stage right over here, and then in front of the stage there are some rows of seating. Maybe the first row has 20 seats in the first row, so that maybe goes from here to here, and then the next row has 3 additional seats, and every row thereafter has 3 additional seats as compared to the previous row. So the next row has 20 plus 3, which is 23 seats, so it's a tiny bit wider, and then the row after that has 26 seats, 3 more than 23, and so on. Now the key to this problem is to notice that we're just adding 3 seats each time, plus 3, plus 3, plus 3, so on. And so if we interpret these seating numbers as entries of a sequence, say 20 is A1, 23 is A2, 26 is A3, corresponding to the rows, then we have an arithmetic sequence. And we know that the formula for an arithmetic sequence is given by an equals a1 plus n minus 1 times the common difference. Now there's some things that we already know about this sequence. First of all, A1 is just 20 because the first row has 20 seats. So we can go ahead and just stick in 20 for A1. Just to be explicit, why don't we write it over here? A1 equals 20. And we also know that the common difference here is 3. That's what we're adding every single time. Plus 3 plus 3 plus 3. Each row has 3 additional seats. So D equals 3. Common difference is 3. So let's go ahead and fill in the rest of our rule again, but with these new values plugged in. So an equals 20 plus n minus 1 times 3. Now the question we're after is how many seats will the 12th row have? So we want to go all the way to the 12th row, which is just A12. And in order to figure out what A12 is, we can just use this rule and plug in n equals 12. Plug in n equals 12, we get that A12 is just 20 plus 12 minus 1 times 3, which we can just go ahead and compute. So that's 20 plus 12 minus 1 is just 11, and then that times 3, which means it's 20 plus 11 times 3 is just 33, and 20 plus 33 is 53. So there we go. That's how many seats the 12th row has. 53 seats. Alright, here's the next problem. Tom's website is growing in popularity. He originally had 4 visitors in the first week, but each week since then, the number of visitors has been 37 more than in the previous week. Assuming the number of visitors per week models an arithmetic sequence, on what week can Tom expect 4,000 weekly visitors? So he originally had 4 visitors in the first week. Let's write that down. 4, and then each week since then, the number of visitors has been 37 more than the previous week. So week 1 was 4 visitors. Then to get to week 2, we have to add 37. And 4 plus 37 is just 41. And then to get to week 3, we have to do the same process, add 37, because that's what it increases by each time, and here we get 78, and then we just keep on doing that some number of times until we get to 4,000. So the question is, on what week do we get to 4,000? Well, why don't we set up an equation to tell us the number of visitors at each week? And that's just an arithmetic sequence. So let's write down the template for an arithmetic sequence. We have an equals a1 plus n minus 1 times the common difference. A1 is just what we started with, 4. And then the common difference is what we're adding every time, so plus 37. Now we can just go ahead and fill in the rest of our sequence. an equals 4 plus n minus 1 times that common difference of 37. Alright, now back to what we're trying to find. We're trying to find on what week can Tom expect 4,000 weekly visitors. So basically, for what n is an equal to 4,000? Well, we have a formula for this now. So why don't we just go ahead and stick in the formula. The formula is just 4 plus n minus 1 times 37. And we set that equal to 4,000, and now we've got an equation that we can solve for n. So why don't we go ahead and do that? Subtract 4 from each side, get n minus 1 times 37 is equal to 3,996. If we divide both sides by 37, we just have n minus 1 is equal to 3,996 divided by 37. Punch that in on a calculator, you get 108. And now we just need to add 1 to both sides, get n equals 109. So there we go. On week 109, that's when Tom can expect 4,000 weekly visitors. Alright, last example. A music festival that started 15 years ago has been consistently increasing the ticket price each year. The price in the most recent year, which is the 15th year, was $335, up from $315 in the previous year. Assuming the ticket price follows an arithmetic sequence, how much did a ticket cost when the festival was founded? Alright, so this time we're given the very end of the arithmetic sequence, the 15th year. So let's write that down. 15th year was $335. And then the year before that was $315. So let's write that down. 14th year was $315. And now we have to backtrack all the way to get back to the first year. And that's what we're looking for. What was the price in the first year? We're going to be modeling this as an arithmetic sequence, so let's write down that template. an equals a1 plus n minus 1 times the common difference. Now let's see what we know. So we can find the common difference from this. The common difference is just the difference between terms, and we know that to get from 315 to 335, we're just adding 20. So there we have d, the common difference, is 20, and we can plug that into our template. Is there anything else we know? We're trying to find a1, so it'd be nice if we could plug in for n and an, and then a1 would be all that we have left, and we can solve for that. So what can we choose for n and an? Well, we have two entries right here. Why don't we use n equals 15, and a15 is $335. So we'll plug that into our template here. A15 is $335, and that comes from plugging in n equals 15. So we'll have 15 minus 1 here. And now we have an equation that we can solve for a1. Note that you could have just as well plugged in a14 equals 315. That should come out to the same result when you solve for a1. We're just going to use a15 equals 335 here in this example of a solution. Okay, so now we're solving for a1. Let's go ahead and simplify this equation. So 335 is equal to a1 plus 15 minus 1 is 14, and then 14 times 20. So 335 equals a1 plus 14 times 20, well 14 times 2 is 28, and then just put a 0 on because we're multiplying by 10 for 20. And now we can just get a1 by subtracting 280 from both sides, and we get that 335 minus 280, that is just 55. So 55 equals a1. So there we go. The ticket price when the festival was founded was just $55. Now we know how to apply our knowledge of arithmetic sequences to solve some real-life word problems. In the future, we'll also learn about another type of sequence, the geometric sequence, and see how it too can be used to solve real-life word problems.